So we're gonna cover causal inference this week. So in the book, I don't have a chapter on causal inference. So hopefully we can cover more on this topic in the class next semester. But this week it'll be just introduction. So I used Koshuke my at Harvard and Mary Davidian and NC State University. They have lectures available, so I use that a little bit. Okay, so we are interested in finding a causal relationship, not association, right? So correlation, association is just a correlation, but causal is more like a direct effect. For example, so these are some examples. So for clinical trial, we are very interested in what's the effect of the new drug, right, on health outcome or disease. Another one. So in economics, one of the typical question is whether a particular job training is really helpful in improving the employment status, so getting a job. So politics, whether canvassing is kind of a political campaign, okay? So suppose you have a political campaign, Iowa State University, then will that really improve the vote turnout? So increase the rate of the participation. So this is, ideally, we want to, so for example, clinical trial, usually they do a randomized experiment, right? You have a randomized and then assign the treatment and control. So that's a pure randomization experiment. But labor economics, we cannot really apply this randomization, right? You cannot really randomly try a person to one, right? You cannot really force one, or smoking, for example. You cannot really randomly force someone to smoke and as others for quit smoke, right? You cannot really do that, right? So that's not possible. So that means some cases we can do real experiment, but for some other cases, we cannot really do the experiment. We just have the observational study. So that's the more challenging. And then, so we want to use A. So it's kind of delta in our notation, but we use A for causal inference. So you can see it's action, okay? So treatment or control. And outcome is Y. So the main key concept is that we have two potential outcomes for Y. So Y0 is the outcome for A equals 0. And Y1 is the outcome, potential outcome for A equals 1. Okay. So this potential outcome concept was first introduced by Neumann, George Neumann, in his PhD thesis. So he was a student at the time at Poland. And so he was a PhD student at Poland. And so his thesis was written in Polish. But he later become scouted to UC Berkeley as a professor. So he's a department. I mean, he's one of the founder of the Department of Statistics in UC Berkeley. And also his contribution. So you heard about Neumann, right? Neumann, Pearson, lemma, right? So he actually has a 3 contribution. One is the causal inference. Foundation of the foundation of causal inference. Second one is the sampling, random sampling. So he make the fundamental foundation of why random sampling is better than purposive sampling. So before him, government usually use purposive sampling, no random sampling. So purposive sampling is you imagine what is the miniature of the population. Okay, you have a population, and what is the kind of average? And then try to investigate those purposive sampling. It's very subjective, right? If you think about that. But he actually showed, so in his paper, JLSSB paper, he rigorously showed that why random sampling is better than purposive sampling in many cases. So that is actually quite. So he made a foundation of the random sampling. I mean survey sampling too. And third one is the hypothesis testing. So he built the foundation of the hypothesis. So his contribution is a lot. But when he come up with this idea, R.A. Fisher didn't really buy his idea, and R.A. Fisher was very famous and arrogant, and so he didn't accept that. Well, he didn't really convinced about Neumann's argument, but these, at least in these three areas, Neumann was correct. Anyway, so this he in his PhD thesis he made this foundation, and this particular chapter was translated to English and published later in 1990. So as a in statistical science. Okay. And randomized experiment or clinical trial, we use the real pure random mechanism, right, to assign who is going to be selected as a treatment group and who is going to be selected as a control group. So that's a pure randomized experiment, like clinical trial. In the observational study, we don't have that. So we just have we observe, right? So we don't. So A is not really under the control of the experiment, right? It's controlled by other factors. For example, physician's discretion. So the physician may just give a direction to particular drug, right? And then just so observation study is more difficult because it's not really randomized. Okay. So fundamental. Okay. So this is the data. So in the data we observe X and A and Y, where Y is a outcome of the particular action choice of your treatment, right? So that means we observe only one potential outcome for each unit. So we either observe Y0 or Y1, right? And so it is essentially a missing data problem. And in some literature, the unobserved potential outcome. So unobserved potential outcome is called the counterfactual outcome. So counter to the fact, right? So this is the actually counterfactual outcome. So the concept of counterfactual is not really from statistics. It's from philosophy. So in philosophy, they have some. There's an area about this causality by Hume and all. So philosophers are always interested in this kind of concept, and they use the counterfactual outcome terminology. But a potential outcome is a terminology introduced by Neumann. Okay, and because we statisticians, we are statisticians, so we want to follow Neumann than philosophers' terminology. Okay. Anyway, so here's the intuition, right? If we could observe, so counterfactual, okay, if A equal to 1, so so for unit I chooses 1, then we observe yi1, right? Only, and yi0 is not observed. So in that case, y0i is the counterfactual outcome for unit I. So intuitively, we could observe the counterfactual outcomes if we could, right? If that's not true, but suppose, right? Suppose we observe it, then we observe both, so that we can compute the difference. So that is this particular difference should be attributable to the treatment effect, the effect to treatment, right? So causal effect. So that is tau I. So that is what we are interested in computing, but that's not identifiable, right? You cannot really observe one over the two. You don't observe one over the two. So the unit level causal effects are difficult to estimate. So the idea is we want to compute. Maybe we can compute it in the population level or sample level. So here's a one set sample average. So sometimes we have this. So average treatment effect is the parameter, but to be rigorous, we have two different concepts: sample level or population level. Okay, so population average treatment effect is purely the parameter, right, in the population, while sample version is actually estimator, but we don't really observe this compute the estimator from the sample because we only observe. So we observe only one. Right? So we observe only one of them, so we cannot really compute the set. Right? This is so you can. It's like sample mean. So this is the estimator, right? This is an estimator of population mean of Y under no missing data, right? But this is so without missing is this is the estimator, right? But but in the missing data literature, we have a missing data, so we cannot really compute it from the observed data only, right? So that's kind of thing we are. So this is the concept corresponding to zeta hat n. You can see that. And another, so average treatment effect is just one particular parameter, and there's another parameter. And sometimes in econometrics, we cannot really make a individualized treatment, right? In the policy, in the economics, they just have a policy. So whether it's just apply the policy to the community or not, you cannot really do. So then everyone applies to the policy or not applies to the policy. So then in economics, maybe they are more interested in what's the effect of the choice if we decide to choose the policy. So that is average treatment for the treated. So that's another concept. So basically the meaning, right? This is slightly something. So we are only, so this guy is just computing the, given that A equal to 1, what is the effect of the causal inference? So that is the basically examples of the parameters. And another parameter, maybe, which is actually quite hard, is that rather than computing the average, so when you compute this average, you are implicitly assuming that population is homogeneous, right? But population sometimes is not really homogeneous, and we may want to compute it in the subgroup level, subpopulation level. So basically, if the population, so the effect, right? So population is not just so I'm not just saying that population is heterogeneous. It's actually the effect is heterogeneous. Okay, the causal effect can be so. So for example, certain drug may be effective to young female than male, for example, right? So then this is very actually important, could be very important, especially in the pharmaceutical company, if they can develop a method, works very well for certain group of people, right? So this is sometimes called precision medicine, and that is actually very hot research area in these days. And sometimes it's called the micro targeting. I mean, depends on which area you are working on. So basically, the concept is we are interested in computing the average treatment effect conditional on X, right? On the subgroup. So X can be demographic, like age group, gender, race, and something like that. Okay. So that is the basic introduction. And now here's a formal statement. So data is assumed to be IID sample, right? So we have this data observation. And we wish to estimate the causal parameters, such as the average treatment effect from the observed data. And so question is, what kind of assumption do we need, right? I mean, when we deal with this kind of problem. So Rubin is made a fundamental foundation on this area. So I'm gonna, and this is a review paper in JASA on his way of describing the basic concept. So you might want to check if you are interested. Okay. So the very first assumption is sometimes called SUTVA, stable unit treatment value assumption. Okay. So what is this SUTVA? Well, basically it's a relationship between your observation, right? This is your observer. And this two is a potential outcome. Right? So you have, I mean, for each individual, we conceptually have two potential outcomes, right? And so we just observe one of them, depends on, one of the two depends on my choice of A, right? So that's actually, very trivial assumption, some sense. But to be rigorous, we need this assumption. So basically, the meaning is that the outcome of YI, who received treatment AI, is the same as his potential outcome for the treatment for that treatment, regardless of the conditions under which he received the treatment. So, for example, the observed Y for treatment A equal to 1 in a randomized clinical trial is the same as the outcome he would have if the same treatment was obtained at the discretion of his physician. So the point is that whether this particular person chooses A equal to 1 by random mechanism or by doctor's recommendation doesn't matter. Okay, so the value doesn't change. The value of Y doesn't change whether he chooses A. So there's no real interference of AI to the counterfactual outcome. Some sense, right? So it implies no interference. So potential outcomes from on individuals are unaffected by treatment received or potential outcomes of other individuals. So we just accept this condition. I mean, mathematically it's trivial assumption, right? Just equation 1. That's it. That's you can just use it as a definition of yi. So, okay.
So, I couldn't understand how this assumption is implied by equation.
I'm sorry?
So, how the assumption of no interference is implied by equation I?
Well, yeah. So, I mean, I don't know either. I mean, causal inference has historically has a lot of confusion. It's a concept. And so what Rubin tried to do was to write it. So causal inference was like, investigated by philosophers before. The philosophers do not have a mathematic concept, right? I mean, they just make concepts even more difficult, right? And so what I think what Rubin tried to do is by just defining this way, that means conceptually you just have two possible choices, two potential outcomes for one. But this is actually could be a strong assumption. Suppose usually if you have a measurement error, I mean, if well, no, well, so basically, if you know, right? So if this is given, y0 and y1 is given, I think this is just a simplifying the problem. Is basically it's just a tool for simplifying the problem. So you originally just observe yi and ai, right? But you want to derive from this one. So you just so from here you basically compute. So you just say that, right? Your observed yi is equal to the realized value of the counterfactual outcome corresponding to your choice. Okay, and nothing else. I mean, okay. So I mean, I think this is just a simplifying concept and to make all the algebra doable. So we'll see why this is reasonable. So I'm gonna introduce this. So we'll use assumption 1 and okay.
Huh? It is saying that so if there are 10 people, 5 people receiving treatment A and 5 people in the control group.
Okay.
So these 5 people will not affect this 5.
Right.
So the outcome will be the same. Individual outcome will be the same if they are receiving treatment A or not. So in that case, it is more interference. One group is not affecting the other group.
Right. I mean, okay. So you just, I mean, this is really. So each one has two values, and no matter what others choose, right? Whatever I choose A equal 1, or AI equal to 0, then I just observe this one or I observe this one. That's it, right? And no, I mean, what others choose, someone else. So AJ equal to, I mean, we are already start with assuming IID. So I don't see any real reason why we wouldn't assume interference at all in the beginning, in the first place. But we'll just accept this assumption one as mathematically and see what statistical result can be derived. So here's the one main result, which seems to be trivial, but it's not really trivial. So basically, if AI is independent of the potential outcome, which is the A1. So remember, this one is different from Y equal A. Y is dependent on A because Y is a function of the A, right? So Y itself is a function of A. So we cannot say that Y, so this is not true, okay? But this could be true, right? This could be true. That means you just flip the coin and decide which one you want to look at, right? Essentially. So under this, so that is the basically randomized studies. So in this case, we can obtain this as a result. So remember, this is a little bit confusing in the beginning, but we'll see. Okay. So how to prove it? Well, I have a problem with my Apple Pencil. So I will. Okay. Yeah. So well, you can put it. Well, I'm sorry, I should. So even A equal to A equal to Y1 A plus 1 minus, sorry, Y0 1 minus A, even A, right? So this is suitable assumption. This is suitable. And then secondly, A equal A, that means we just have one. So if A equal to small a equal to 1, then it's just Y1. If small a equal to 0, then it's just Y0. So this is equal to this, right? And then this is equal to YA. Why? This is the assumption 2. I don't know whether you guys can see. You cannot really see this. Sorry.
The last line is from the second assumption.
Huh?
The last line is from the second.
Last so by assumption 2. Okay. So that is the result. So that means what? That means so this is basically the right side is what you are interested in computing the right side, because you are interested in computing the difference between y1 expectation minus y0 expectation, right? So you are interested in computing this one, but you don't observe y8 directly. What you can observe is only y. So that means you can basically, so what this result is that you can just compute the conditional expectation of y, observe the y, given among the group, right? And use that to compute the counterfactual mean. That is the basic idea. So that basically is the justification. So the implication, so the interpretation of result 3 is that you can basically, so the right side is what you want to compute, but you can use the left side to compute its estimator. So that means you can use the sample version of this. So equation 4 is just the sample, the mean difference of the samples, right? So the first one is the sample mean of y's in among a equal to 1, while the second term is the sample mean of y among a equal to 0, right? So basically it's just the mean difference, right? So difference in means estimator. So the difference in the mean estimator is written in 4, but because of the Sutba, so use under the Sutba assumption, we can write. So basically, yi is a ai times, right? So see this yi is a function of ai, right? ai times y1 plus 1 minus ai times y0. So apply to that, you get this expression. So second expression is written in terms of the counterfactual outcome, right? While the first one is written in terms of the original observation y. Okay. So now remember, in this case we are essentially randomizing, right? We use AI so as a sampling indicator. So we can treat the counterfactual outcome as a finite population. So y0 and y1 pair. This one is your finite population, and then the randomness is only AI. Okay, so that is a sample indicator. You just choose. So AI equal to 1, you observe this. AI equal to 0, you observe this, right? So then you have a basically sample, 2 sample mean estimate. So then under the randomization distribution, treating Fn as fixed, we get, so then the only thing is random is AI, capital AI. So your AI you take the expectation. And then what is the expectation of AI? That is N1 divided by N. Right? It's just a simple random sampling, essentially. So you basically have a N1 cancelled. So this one is N0 cancelled. So you get SAT. So that's the expectation. Okay, that is the expectation. And now we can use it. Same way we can compute the variance. So the variance is computing the variance is not that simple, but it's doable. So the equation 5 is the result of the computation to sampling, where so you have a S1 okay, S1, S0, and okay, S1, S0, and S01. Okay. So basically, S1 square is the sample variance of the Y1s. Okay. So now how to compute? By the way, this is kind of population sample variance and population variance, population covariance. So you cannot really observe this, right? Because in the sample you either observe this guy or this guy. So it's not really, you cannot really compute this. So that is a very intriguing problem. And so we'll see how to solve this. So let me, I think I have some problem. So sorry, let me, I can maybe use the slide. Share. Okay. Let me share again with my, okay. So, yeah, this is, so I just, so equation 5. So how to compute the equation 5? So I'm going to show you, explain briefly. Okay. So we are interested in computing the sampling variance. Okay. So we are interested in computing the sampling variance of tau head. And tau head is this guy, right? So this is a sampling indicator, essentially. So how to compute the variance of these guys? So that is actually step 521 problem. But we'll briefly take a look how we compute it. So basically, it's we treat small n as a finite population size, capital N, and N1 corresponds to sample size. So you are selecting N1 samples from small n, and this is the indicator. And so these A's are all equal. So that means this is all equal. So then the expectation is N1 divided by N, right? So just a sampling rate. Okay. And then you take the square both sides, and then simplify. We know that they are all equal probability. So this end of the day, you get something like this. I think that this is basically gone. Okay. And then, so this is basically a sampling indicator, and then your covariance. So this is, so then what is the covariance? I equal to J, I equal not equal to J. You get this. Well, if you, so if you show this, then from here to here is just easy, right? Because this is the, what is the covariance of two random variable? This is the expectation of the product minus product of expectation, right? So basically you can get, and then from there, you now want to compute the each one. So in tau hat, remember in tau hat, this is the first component of tau hat. And so you want to compute the variance. So then first of all, you subtract by constant, and which is essentially no sampling error, because summation of AI is or equal to n1. And then the only random variable is AI. So this is basically you have a linear function of AI. So you can compute the covariance variance of the linear function easily. So this is the variance part. This is the covariance part. Okay. And then simplify. So, and this double summation, well, at least I can write it in the board. So this kind of algebra is should, so okay. Well, I have some time. So let me quickly show you how you compute all this. So this is basically AI equal to N1, right? So from here, you can basically compute the AI square plus, which is AI. 0 and 1 square is same, right? And then double summation. Right? So that you can actually compute. So you take the expectation, then you have n over n1 plus right? So that you can get so that's how you get this, the first result. The second one is easy. And then now, so this part should be easy, just a constant. And then from here to this part, basically you, what's this? So basically you can write it as a N1 over AI zeta. So you can write it as a Y1I. So that is actually variance of AI zeta square plus variance AI Z1, Z, right? So you can get all this. So you now have a F1 minus F, right? Summation I square. And then if you do that, then you have a N minus 1. And this is so that this is summation ZI square minus. So you end up getting, so this 14 basically right, you have all this and then n over. So this guy times this guy is equal to this. So you have a n1 over n over times n ci summation ci square, and then square. Something like that. But this summation is 0 anyway in the beginning, so it doesn't really matter. So only first one matters, and then you can basically obtain this one. Simplify. Okay, and then so finally, the last covariance term, you can essentially get this one. It's same thing. So and then the covariance. So then the only random variable is AI and 1 minus AI. So this is actually becomes a double summation, and then covariance AI and 1 minus AJ and something like that. And this guy, so covariance AI 1 minus AJ is equal to what? Minus covariance AI AJ, right? And then that's basically exactly corresponds to so you can where, and then you get then what you so that means the final term is equal to the second last term is equal to minus of the n1 inverse n2 and n0 inverse of the double summation and j equals 1 to n covariance AI AJ Z1 0 and Z1, right? But we already computed this double summation before. We already completed this double summation, right? We already completed this double summation here. This is actual double summation. So same thing. So you can eventually obtain the covariance of this term plus times some constant, which you can check. But yeah. Oh, sure.
Just slide 14.
14?
14.
Okay. Okay, sorry. Okay.
These expectation and covariance, these are conditional expectations. Right?
Conditional, right? Yeah. Right. Conditional on so on count of right. I mean conditional on the potential outcomes. Right. Okay. So yeah, that is just all the algebra deriving equation 5, right? Deriving the sampling variance of the tau hat. And now, so this is the very weird form, right? We have something like this. And then what should we do with this? I mean, how to estimate this? So Neumann's idea, okay, Neumann's idea is, okay, his idea is that we can estimate S1, we can estimate S0 square, right? S1 square, S0 square, but not this covariance term. So his idea is, okay, what is the upper bound of this covariance? Okay, the upper bound of this covariance, population covariance, will be this, right? That because of the, if you think about the correlation is equal to 1, right? Then you will have this upper bound. So that means you plug in, so let's consider the upper bound. So once you obtain the upper bound, then algebra, you get this one. Okay. So this is the upper bound. So that this upper bound holds when correlation between y1 and y0 is equal to 1. And now the second inequality, so but this one is also upper bound, has an upper bound, something like this. Why? You can use the Cauchy-Schwarz inequality again. So, okay, how to do that? Well, S1 squared divided by N1 plus S0 squared divided by N0. Okay, sorry, that is the, okay. We have this one. So S1 and 0, N1, S0 divided by N0, right? S squared. And you have what? S1 squared, N1, S0 squared, N0. Right? And so what is the right N1, right? You have this one, right? So this is the upper bound. Cauchy-Schwarz. So and then this guy can be moved here. Okay. So that is basically this one. Okay. So that's interesting. And then what is this, by the way? This one looks familiar, right? This one is S1 squared by N1 plus S2. So that is kind of the denominator in the T statistic, right? Essentially. So that is a usual variance formula. And so the Neumann's claim is that if you use the usual variance estimator treating two samples are independent, then you are essentially making a conservative variance estimation. So conservative means that it overestimates the true variance, but you never really get lower, right? In expectation. So that means it's acceptable. I mean, you got wider confidence interval, but still, you are okay. Then so conservative means you have a wider confidence interval than necessary, but still it covers the truth, right? Right. So if you do this, your 95% confidence interval will cover at least 95% on average. So that in that sense is acceptable. So that is his idea.
And what is the, so you said independent sample,
So okay, yeah. So independent. So tau hat, yes. Tau hat is nothing but y1, right? So nothing but this. So if you, even if this is a randomized distribution using some very complicated sampling theory, but the variance, end of the day, your variance estimator, which is very difficult to compute, but can be, if you use simply sigma 1 square divided by n1 hat plus sigma 0 hat square by n 0 hat, I mean something like that, then it is actually greater than or equal. So it gives an upper bound of the true sampling variance.
yes, so my question is under the equality, what can be said about, what can be said under the equality? So y1 and y0 are independent.
Correlating. Correlation one.
Uncorrelated.
Right. So for example, in correlate, so perfectly correlated. So in his paper, so it's like but that is very, very C, right? So if you have this kind of situation, so you observe only one of the two, but suppose your population actually have this kind of linear relationship, then your upper bound has this equality. Like that. Okay. Okay, so that is the basically Neumann's idea. And now here's one more argument. So now this is for sample difference in estimator using the randomized distribution only. But if you are interested in the population average treatment effect, then your population average effect means that you are interested in computing the difference between mu y and mu 0. So this is your parameter. The difference between the two is the parameter. So that you assume a model, superpopulation model. So superpopulation model of the counterfactual outcome. And then once you generate this finite counterfactual outcome, you randomize. Right? So it's a two-phase sampling structure. Phase one, you generate the finite population. You generate the counterfactual outcome. So bivariate data, right? Bivariate, you generate the bivariate realization of the y0 and y1s over I equal to 1 to n, right? So that is the complete sample. But in practice, we don't really observe both, right? So then we choose. So that is the second phase. Second phase is a select treatment group by simply the sampling of size n1. Okay. So then the overall distribution, right? The random distribution should be joint over the two. So generating the sample and then randomize. Okay. So that is the very rigorous treatment of what's going on in the randomized experiment. And then we are interested in computing this estimating the this parameter from the sample obtained from this two-phase sampling structure. And then, oops. Okay. And then the answer is that you can just use the same estimator to estimate the population parameter, and then variance, you have a very nice form, right? So this one is much better, right? Looks less ugly than the previous one. So remember the previous one, this guy is the variance conditional on F. So that's a conditional variance. That means it's conditional on the first phase sample, right? And only randomized second. But if you combine the two, so that means, so that I wish I can, yeah, sorry. So bad, but so that's very fundamentally important, is that if you rigorously apply this two-phase structure, so then the variance should be expectation, so variance of the conditional expectation, right? Plus expectation of the conditional variance. Right, so let's look at this. Then the first one is the expectation of the conditional. So expectation of the conditional expectation is nothing but SATE, right? Because in the second phase, so the second phase, you average it, you get SAT, which is the complete sample estimator. And I equal to 1, 2, y I1 minus, can you see this? Right? So this is SATE. And then expectation of the conditional variance. So conditional variance, we already know the conditional variance is, we already derived this. N1 over N, N1, N0, S1 square plus N1, N0, S0 plus 2 times S01, right? So then what is the SATE? So variance of this guy is, so there is 1 over N. Sorry, this is should be N, right? So that is basically variance of 1 over N times variance of Y1 minus Y0. Okay. So that is what? That is 1 over N S1 square plus S0 square, and sigma 1 square plus sigma 0 square minus 2 sigma 1 0. Right? So this guy is cancelled with this. Okay, because this S0, this is 1 over N 2 times S01, right? But this one is minus 1 over N minus 2 times sigma. So this guy cancels, and then this guy and this guy combined together gives the what we want, right? Gives the so this is basically 1 over n 1 minus 1 over n. So n divided by n1 minus 1. And so you end up getting this variance. So this variance. If you combine the two. So in that sense, the upper bound perfectly makes sense, right? Because our previous conditional variance is just the one part of the total variance. Okay. So that is the basically the main message. So basically this is, yeah. So this kind of framework is very rigorous treatment of the how you can interpret the randomized experiment using the counterfactual, I mean the causal potential outcome framework, right? But this one is based on the second phase is actually the sampling. Second phase is the sampling, which is simple sampling, which is essentially randomization part, and which is our under control, right? We randomize, and so it's not really surprising why Neumann developed the sampling, because when we consider this experiment, randomization experiment, naturally this idea is evolved to agricultural survey. So actually, his thesis is the title of his thesis is on the application of the probability theory to agricultural experiment, and that becomes later becomes how we can use sampling ideas to get unbiased estimation. Very fundamental idea. So that's the main thing. And I will Thursday. So today I covered mainly about the experiment, randomized experiment, and how to do causal inference with the randomized experiment. And then Thursday we'll cover observational study. So, okay. Any questions? Yeah, sorry, I couldn't, somehow my Apple Pencil is broken, so I may include a derivation in the lecture note and update. Yeah. Okay, that's it. See you Thursday.